Let's treat more questions on vector spaces. So we'll be looking at another question on vector spaces, and this time around it's going to be a three-dimensional Euclidean space where we have x1, x2, x3 plus y1, y2, y3, which will give us x1 plus y1, x2 plus y2, x3 plus y3, where our scalar is kx1, kx2, as3 when multiplied. So we could see in our scalar multiplication that the rule is only for dimension x. So it's one dimensional. So let's prove. So our first property in our definition of vector space is closure property. So for every u, v that is in V, u plus v is also in V. So in this scenario, we have x1, x2, and x3 to be u, and y1, y2, and y3 to be v. So we could also say, since it gives rise to a three-dimensional Euclidean space, it means u plus v is also in V. So the second one now is commutativity. So here we have u plus v is equals to v plus u. So we already know what u plus v is in the vector addition given to us. So when we compare our results for v plus u, it is also the same because only the positions are interchanged, and addition is commutative because y1, x1 plus y1 is the same thing as y1 plus x1, and x2 plus y2 is the same as y2 plus x2. So we can see that it is commutative. So the third one now, we need a zero vector in three-dimensional space such that we have 0, 0, 0, and this property is known as the additive property, where when you add u plus 0, it also gives you u. So in this instance, when you had x1, x2, x3 plus coordinate 0, 0, 0, it gives you a what? Back the first vector, that is u plus 0 is equals to u. So the second vector in addition to the vector vector gives you the vector vector back. So u plus v in this instance, where v is 0, it gives you u. So that means our y dimension now is 0, 0, 0. So that is for our additive property in three-dimensional Euclidean space. So our fourth property is the additive inverse. That is, for every u, we have a negative u, such that when you add these two together, it gives rise to 0. So here we could see that the property holds. So x1, x2, and x3 plus minus x1 minus x2 minus 3 give us 0. So this property also holds. So as far as we are, none of this property has been proven wrong. Thus, we need to search for more properties to see whether it's a vector space or not. So as long as all the 10 properties hold, it means it's a vector space. So our fifth property is associativity of addition. So in this instance, u plus v in brackets plus w is the same thing as u plus open brackets v plus w in brackets. So we look at that here, where x coordinate is u, y is v, and z is w. So we then add by saying, okay, u plus v, now that is x1, x2, x3 plus y1, y2, y3 for our left hand side in brackets, then z1, z2, z3. So this is for our left hand side, that is u plus v in brackets plus w. So w in this instance is z coordinates, v is y, and u is x. So now to give rise to what we have here, it gives rise to what we have. We have x1 plus y1 plus z1, x2 plus y plus z2, x3 plus y3 plus z2. So that is what we have. Then let's see for our right hand side to see whether it's equal. So for our right hand side now, it is u coordinate, it is u that is outside the bracket. So we have u plus open bracket v plus w close bracket. So we also see that we have x1 plus open bracket y1 plus z in bracket, x2 plus y2 plus c2, x3 plus y1 plus c3. So opening the bracket, we could see that when we compare equation 1 and equation 2, we still have the same thing. Thus, it obeys the rule of associativity. So it is a vector space since it obeys associativity. So we still have several other properties that we can look at. We have the two distributive properties. So I feel you can try this on your own. You can try out the distributive properties, in which the first one that we have is u plus v, in brackets then scalar e is equals to au plus av, and then the other one we have is that for scalar, where we have a plus b in brackets then u, which gives rise to what? It gives rise to au plus bu. So these are the two distributive properties we have. One is for scalar, one is for vector addition. So the vector addition is u plus v in brackets then a. Right, for the scalar is a plus b in brackets u. So in these instances, what you just need to do is represent your a plus b as k, and remember it's only multiplying the x coordinate according to the rule given. Your k is only to multiply x, it is not to multiply y. So let's call that all for today. So in our next episodes, we'll proceed into subspaces, and then we'll also look at more questions on subspaces and vector spaces and several other examples of vector spaces. So for this, in our next class, I'll be dropping the solution, or rather I will be dropping the solvents of a distributive. So for those of you attempting now, you can see through what you have done, whether it's correct or not. So as for the question given, the question is actually the vector space given the 10 conditions are all met. As long as the 10 conditions are all met, it is a vector space. So whatsoever workings you might do now, just keep it in mind that if you have a situation where it doesn't obey one of the laws, it's most likely that it is not a vector space, provided that there are no errors in your calculations. So next episode we'll drop the answers for that, and then we'll do the distributive. Goodbye.